will discuss about kinematics of rigid bodies in engineering mechanics. So before starting the kinetics of rigid bodies, we have to know some definitions. So what is particle? The negligible mass is called particle. And coming to body, any piece of matter is termed as body. And rest, a body does not change its position with respect to its surroundings, is called a rest. Body, when the body changes its position with respect to its surroundings, is called the body is in motion. So coming to kinematics of rigid bodies, the course objective is to understand the kinematics and kinetics of translational and rotational motion of rigid bodies, and the course outcome of this one is solve the problems involving the translational and rotational motion of rigid bodies. So okay, and so kinematics of rigid bodies. So what is kinematics? It is that branch of dynamics which deals with the motion of the bodies with considering the forces causing the motion. That is the kinematics. Okay, and coming to rigid bodies, a rigid body is forming a large number of particles occupying fixed positions with respect to each other. That is a rigid body. Okay, and this kinematics of rigid body, a rigid body forming a part of mechanism which has fixed length whatever its motion. Therefore, any 2 points on the body will remain fixed distance apart. In the plane motion of a rigid body, all the particles will move in parallel in plane. Okay, and coming to types of rigid body motions, motion of translation, motion of rotation, first one is motion of translation, and second one is motion of translation, and third one is curvilinear translation. General plane motion of translation, and second one is motion of rotation, and third one is general plane motion, that is motion of translation and rotation. And coming to motion of translation, in translation motion all the particles move in parallel paths. All the particles move in parallel paths, and the straight lines are joining arbitrary points on the body remain parallel throughout the motion. See here the types of translations, rectilinear translation and curvilinear translation. In rectilinear translation, all the paths are in straight lines. If the paths are in curved lines, then the motion is said to be in curvilinear motion. Okay, here rectilinear motion, see the paths are in straight lines, and curvilinear motion the paths are in curved lines. Example of this one is motion of piston in IC engine. Motion of piston in IC engine, that is the example of rectilinear translation. Coming curvilinear translation, example of curvilinear translation is motion of connecting link of a locomotive. See here, this is the rectilinear motion, rectilinear translation. See these 2 points are joined on the body. These paths are straight line paths, line joining the arbitrary points are parallel. This is the rectilinear translation, and curvilinear translation, here the paths are in curved lines. See some examples of rectilinear translation, some examples of rectilinear motion from our daily lives. On a track, an athlete is running. A bead that moves along a fixed rod. On a straight track, a train is moving. Parallel swimming by 2 swimmers. Examples of curvilinear motion is motion of a snake, a roller coaster, a train moving on a curved track. So these are the examples of translation, rectilinear translation and curvilinear translation. And next, motion of rotation. The motion of rotation occurs when all the particles move in concentric circular paths with common center. The center may be in the body or outside the body. As shown in figure, the axis passing through the point of rotation is called axis of rotation. The point lying on the axis of rotation it is having zero velocity. When the point lying on the axis of rotation, that is having zero velocity. Okay, see, these are the inside the body and this is outside the body. The common example of motion and rotation are motion of armature and turbine rotor. Next, general plane motion. It is the combination of translation and rotation. The common example of general plane motion is motion of a roller without slipping. See here, this is the graph general plane motion. A dash, this is represents motion of translation, it is a straight line, and A dash A1, this is the motion of rotation, they have curved path. This is the initial position, this is the final position. See, A dash is the motion of rotation and A dash A is the motion of translation, that is axis of rotation. And next, coming to circular motion. Coming to circular motion, it is a special case of curvilinear motion. A body is said to be in circular path. Its distance from a fixed point in the plane of rotation is constant. This constant is called a radius, and the center and the fixed point is called center. And next, coming to the fixed axis rotation. Fixed axis rotation of a rigid body is defined as the motion in which the particles of the rigid body move in circular paths with their centers on a fixed axis rotation. See, generally we are using the definitions in kinematics of rigid bodies is angular displacement. See here definitions. The definitions of the important terms which are frequently used in the study of circular path, circular motion, are angular displacement. First one is the angular displacement, the angle through which a body displaced. The angle through which a body displaced is called angular displacement. It is measured in unit radian. Angular displacement theta is equal to omega into t. Angular displacement is generally represented by theta, that is theta is equal to omega into t. Okay, here one revolution is equal to 2 pi radians. And coming to angular velocity, it is expressed in angular velocity. The rate of change of angular displacement of a body is called angular velocity. It is expressed in radians per second and is denoted by omega. The angular velocity is commonly expressed in revolution per minute and converted into radians per seconds. Angular velocity omega is equal to 2 pi by 60, 2 pi n by 60 radians. 1 rpm is equal to, 1 rpm is equal to 2 pi by 60 radians per second, and angular velocity omega is equal to 2 pi n by 60 radians per seconds. And next, angular acceleration, it is expressed in radians per second square. Angular acceleration, it is defined as the rate of change of angular velocity of a body is called angular acceleration. Angular acceleration is generally denoted by alpha. And coming to derivation of rotational motion with uniform angular acceleration, consider a particle moving with constant angular velocity omega radians per second in a circular path of radius r. Let theta be the angular displacement corresponding to linear displacement s in a given time t seconds. See the first equation here, omega is equal to omega naught plus alpha t. See, generally already we learned angular acceleration, it is the rate of change of angular velocity. Alpha is equal to d omega by dt. Now written this one, change in velocity, change in angular velocity dw is equal to alpha into dt. By integrating on both sides, here the lower limit is initial angular velocity and upper limit is final angular velocity. dw is the change in angular velocity, integral 0 to t alpha dt. Initially the body is at rest and time is 0, and finally the time is t. By applying the integral dw means d omega means omega. By applying the limits here, final velocity minus initial velocity omega minus omega naught is equal to, here alpha is constant, integral dt means t. By applying the limits to t minus 0, that is alpha t, omega minus omega naught is equal to alpha t. And next, coming to theta is equal to omega naught t plus of alpha t square. See, angular velocity is equal to change in displacement by time d theta by dt. Then d theta is equal to omega into dt. D theta is equal to, already we found in first equation omega, that is omega naught plus alpha t. D theta is equal to omega naught plus alpha t dt. And by applying the integrating on both sides, 0, lower limit is 0, upper limit is theta. Integral d theta is equal to 0 to t omega naught plus alpha t dt. So here integral d theta is theta. By applying the limits here, theta minus 0, that is theta. Omega naught dt plus alpha t dt. Integral t is integral omega naught is constant, and dt, the integral dt means t. Then we applying the limits to this one, we got omega naught t plus of alpha t square. And the third equation is omega square is equal to omega naught square plus 2 alpha theta. Now here angular acceleration is alpha is equal to angular velocity by angular change in velocity by change in angular velocity by time, d omega by dt. Alpha is equal to, now write this term in terms of d theta. Alpha is equal to d omega by d theta into d theta by dt. Okay, then alpha d theta is equal to omega into d omega. Here the omega is d theta by dt, d theta by dt. Finally alpha into d theta is equal to omega into d omega. Integrating on both sides, 0 to theta alpha d theta, omega naught omega is integral omega naught omega limits omega into d omega. By applying the limits to this one, integral d theta means theta minus 0, then alpha theta is equal to, by applying the limits to this one, integral omega d omega, omega square by 2, half into final omega square minus omega naught square. Okay, this one is omega square is equal to omega naught square plus 2 alpha theta. So these equations are generally used in kinematics of rigid bodies. Omega is equal to omega naught plus alpha t, theta is equal to omega naught t plus of alpha t square, omega square is equal to omega naught square plus 2 alpha theta. These are for rotational motion for uniform angular acceleration. These three equations for uniform acceleration. Omega is equal to uniform angular acceleration. Omega is equal to omega naught plus alpha t. Theta is equal to omega naught t plus of alpha t square. Omega square is equal to omega naught square plus 2 alpha theta. Next, coming to relation between linear and angular motions. Consider a particle with constant angular velocity omega radians per second in a circular path of radius r. Let theta be the angular displacement corresponding to linear displacement s in a given time t seconds. Let v is equal to linear velocity in meters per second, a is equal to linear acceleration meter per second square, and as a linear displacement s is equal to length of arc AB. This is a linear displacement length of arc AB. Then s is equal to r theta. Differentiating this one with respect to t, then ds by dt is equal to r into d theta by dt. Here ds by dt is equal to v, and v is equal to ds by dt means v, and d theta by d theta is omega into r. Again differentiating with respect to t in equation 2, dv by dt is equal to r into d omega by dt. then A is equal to R alpha, A is equal to alpha R, dv by dt is equal, dv by dt means acceleration, and d omega by dt is alpha and R. A is equal to alpha R. And next, centripetal acceleration. In centripetal acceleration, consider a particle move in uniform velocity. The velocity at any point is tangential to the rotation of motion of the particle. Though the speed is constant, there exists an acceleration due to change in the direction of velocity. This acceleration is called centripetal acceleration. This acceleration is directed towards the center. This is a normal acceleration or a radial acceleration. To evaluate the centripetal acceleration, here the body is moving from A to B through a small angle delta theta along a circular path shown in figure A. The velocity diagram B shows that the vector AB represents change in velocity dv. This is directed towards the center. Since delta theta is very small, it may be considered as AB, that is equal to chord length AB. From similar triangles of AOB and small AOB is AB by R is equal to small AB by V, that is AB means dv, change in velocity, dv by V. For uniform velocity, the normal acceleration is constant, and it is given by acceleration is equal to change in velocity by time. So an is equal to normal acceleration, that is dv by t. Then change in velocity dv is equal to an into t. Right, this is the equation 2. And next, displacement is equal to velocity into time. Displacement is equal to velocity into time. Here the displacement is AB. AB is equal to velocity v time t. Substituting these values in the values from equations 2 and 3 in equation 1. Here AB is v into t. Capital AB is equal to v into t. dv is equal to an into t. See, AB is v into t by r is equal to dv is equal to an into t by v. Then an is equal to v square by r. But v is equal to r omega, then an is equal to omega square r square by r, that is equal to omega square r. When a body moves in circular path with variable speeds, then it is given tangential acceleration. Then a square is equal to an square is equal to at square. Then a is equal to square root of an square plus at square. And coming to the equations of circular motion, so in the first equation, angular acceleration is equal to alpha is equal to angular velocity by time, that is rate of change of velocity by time, that is means omega minus omega naught by t. Here omega is equal to omega naught plus alpha t, or t is equal to omega naught minus omega naught by alpha. Angular displacement is equal to angular velocity into time. Angular velocity theta is equal to angular displacement theta is equal to average of angular velocity, that is final angular velocity plus initial angular velocity by 2, and omega is equal by 2 into time t. Here omega is equal to omega naught plus alpha t. Then theta is equal to, instead of omega naught plus, by applying omega is equal to omega naught plus alpha t plus omega naught by 2 into t. Then theta is equal to 2 omega naught plus alpha t omega naught by 2 into t. Then theta is equal to omega naught t plus half alpha t square. Theta is equal to omega plus omega naught by 2 into t. Already we had written in the first equation t is equal to omega minus omega naught by alpha. By applying the t value here, theta is equal to omega naught plus omega plus omega naught by 2 into t. T is equal to omega naught minus omega naught by alpha. See, theta is equal to omega naught plus omega naught by 2 into omega naught minus omega naught by alpha. Theta is equal to omega square minus omega naught plus omega naught minus omega naught square by 2 alpha by multiplying these two. Then theta is equal to omega square minus omega naught square by 2 alpha. See, 2 alpha theta is equal to omega square minus omega naught square. That is the third equation. And write the angular displacement in n second. Theta n is equal to angular displacement in n seconds minus angular displacement in n minus 1 seconds. Angular displacement in n seconds here, okay, omega naught n plus 1 by 2 alpha n square minus omega naught into, apply here instead of n minus 1 plus half alpha into n minus 1 whole square. Here n minus 1 whole square is written as a minus b whole square. Omega naught n plus half alpha n square minus omega naught n minus omega naught into 1 omega naught plus half alpha into, it is written as a minus b whole square n square minus 2n plus 1. Omega naught n plus half alpha n square minus omega naught n minus omega naught plus half alpha n square minus alpha n plus alpha by 2. Omega naught n plus alpha of alpha n square minus omega naught n plus minus into minus plus omega naught minus half alpha n square plus alpha n minus alpha by 2. Then omega naught plus alpha n minus alpha by 2. Here the plus 1 by 2 alpha n square minus 1 by 2 alpha n square is cancelled. Okay, omega naught plus alpha into n minus 1 by 2. Then theta n is equal to omega naught plus alpha by 2 into 2n minus 1. And coming to relative velocity, here the point A is measured from a fixed point or fixed reference is called absolute velocity. Sometimes it is necessary to be considered the point B is relative to another point A that has different motion. If two bodies A and B are moving with velocities VA and VB relatively each other, then the vector difference is VA and VB. If OA represents VA and OB represents VB, drawn from the point O, then AB represents the relative velocity of B to the another B the represents velocity of B relative to A. AB represents velocity of A relative to B, that is VBA. And coming to velocity triangle for a rigid link, consider AB represents a link in mechanism. Here the velocity of A is completely known and the direction of velocity is VB known. For finding the velocity of VB, magnitude of VB and angular velocity of AB is obtained by drawing velocity triangle. See the procedure of how to draw velocity triangle for a rigid link. Draw OA to convenient scale to represent VA in magnitude and direction. Through O, line OX is parallel to the given direction VB. Line OX is parallel to the given direction VB. Through A, perpendicular to link AB to cut OX in B. Then OB represents the velocity of B VB and AB represents velocity of B relative to A, that is VBA. To find the velocity of any point C on AB, locate point C on link AB such that AC by AB is equal to capital AC by AB. The angular velocity of link AB is equal to AB that is angular velocity, it is represented by omega, that is equal to VBA by AB. VBA means AB, AB by AB. VBA by AB is equal to AB by capital AB. See, note here, OAC is the velocity of triangle for length AC, then omega is equal to VCA, AC is equal to AC by capital AC. Velocity is measured relative to O or absolute velocities. Instantaneous center of rotation. Consider a particle. Let us consider a rigid body, a plane motion of a rigid body. Let the velocities V and VB through the points E and B draw perpendiculars to VA and VB through the points A and B. These two lines are intersecting at point C, which is instantaneously at rest and is having zero velocity. So if V and VB are different, then the body must have an angular velocity, omega radians per second. The angular velocity of the rigid body is obtained by the relation omega is equal to AC by omega is equal to AB by AC, VA by AC and VB by VC. So if V and VB are parallel, the instantaneous center is the point of intersection AB with the line joining extremities of vectors VA and VB. Then VA by AC is equal to VB by BC. Suppose if the velocities VA and VB are parallel and opposite, V and VB are opposite, the point C lying on between A and B. See some problems of fixed axis rotation and translation of kinematics of rigid bodies. A flywheel, see the first problem, a flywheel which is at rest attains a constant speed of 300 rpm after accelerating uniformly for 10 seconds. Determine the number of revolutions made by the flywheel during this speed. A flywheel, see here in the problem it is given flywheel is there, it is at rest, it attains a constant speed of 300 rpm after accelerating uniformly for 10 seconds. Then it means initial angular velocity of the flywheel is omega naught is equal to 0. Here the speed is given, flywheel speed is given 300 rpm. Okay, but angular velocity is radians per second. For converting this one, final angular velocity omega is equal to 2 pi n by 60. 2 pi into 300 by 60, that is 31.416 radians per second. Angular acceleration alpha is equal to 31.416 minus 0. Final angular velocity is up to 31.416 minus initial angular velocity, that is 0, that is equal to 3.1416 radians per second square. Then angular displacement theta is equal to, it means it is asking determine the number of revolutions made by the flywheel during this speed. Okay, it is asking number of revolutions. Okay, then angular displacement, number of revolutions means it is angular displacement theta is equal to omega naught t plus half alpha t square. 0 plus half into 3.1416, that is omega naught, that is alpha, into 10 square, 157.08 radians. Here omega naught is 0 time t seconds, that is 0 into t multiplied 0, half into 3.1416 into 10 square, that is 157.08 radians. Okay, it is converted in revolutions per second, 157.08 by 2 pi, then it is revolutions per second. And coming to Next problem, a wheel is rotating about its axis with a constant angular velocity of 1 radian per second square. If the initial and final angular velocities are 4 radians per second and 8 radians per second, determine the total angle turned through during the time interval this change of angular velocity took place. Okay, here it is given a wheel is rotating about its axis with constant angular acceleration, that is 1 radians per second square. Angular acceleration is generally represented by alpha, that is equal to 1 radian per second square. If the initial and final angular velocity it is given, that is initial angular velocity omega is equal to 4 radians per second omega naught, and final angular velocity omega is equal to 8 radians per second square, 8 radians per second. Then total angle turned, here we have to determine the total angle turned, that is theta. 2 alpha theta is equal to omega square minus omega naught square, that is theta is equal to omega square minus omega naught square by 2 alpha. Here final angular velocity, that is 8 square minus initial angular velocity 4 square by 2 alpha, 2 into alpha is 1, 24 radians. And next problem, a wheel rotating about a fixed axis at 20 rpm is uniformly accelerated for 70 seconds, during which time it makes 50 revolutions. Okay, a wheel rotating about fixed axis at 20 rpm. Here the wheel is rotating at a speed of 20 rpm, that is n is equal to 20, is uniformly accelerated for 70 seconds. T is equal to 70 seconds. Then during which time it makes 50 revolutions. Here the wheel makes 50 revolution, then theta is equal to 50 revolution. It is converted into radians, then 50 into 2 pi, 314.16 radians. Then theta is equal to first one it is given angular velocity at the end of this interval, and second time required for the speed to reach 100 revolutions per minute. The first point, theta is equal to omega naught t plus half alpha t square. By applying this one we will get alpha, angular acceleration. Then theta is equal to 314.16, that is equal to 2.09 into times t 70 plus half into, we don't know the angular acceleration alpha, we have to find alpha into 70 square. Then 314.16 plus 146.3 plus 2450 alpha, then alpha is equal to 0.068 radians per second square. In the first bit it is asking angular velocity at the end of this interval. Then omega is equal to omega naught plus alpha t. Omega naught it is 2.09 plus alpha 0.068 into t 70 seconds, 6.85 radians per seconds. Then time required, angular velocity corresponding to 100 revolutions per minute. Then omega is equal to 2 pi n by 60, 2 pi into 100 by 60, we convert in meters per second, 10.472 meters per second. Then omega is equal to omega naught plus alpha t, 10.472 is equal to, here the final angular velocity, that is initial angular velocity is 2.09 plus 0.068 into t. Then t is equal to 123.26 seconds. And go to next problem. A 600 mm diameter flywheel is brought uniformly from rest to a speed of 350 rpm in 20 seconds. Determine the velocity and acceleration of a point in the rim 2 seconds after starting from rest. Here the diameter of the flywheel is given, brought uniformly from rest to a speed, it is starting from rest to speed 350 rpm in 20 seconds. Determine the velocity, acceleration of a point. So we have to find here velocity and acceleration a point in the rim 2 seconds after starting from rest. Okay, radius here diameter of the flywheel is given. Then here radius is equal to diameter by 2, 600 by 2, 300 mm, that is 0.3 meters. Initial angular velocity is omega naught is equal to 0 because it is given, it is brought uniformly from rest. Okay, and final angular velocity 2 pi n by 60. Here the speed is given 350. 2 pi into 350 by 60, 36.652 radians per second. Next, angular acceleration. We have to find here angular acceleration alpha is equal to omega minus omega naught by t. We know the relation here, alpha is equal to omega naught minus omega naught by t. Here final angular velocity 36.562 minus initial angular velocity 0 by time 20 seconds, that is 1.83 radians per second square. Angular velocity after 2 seconds, omega is equal to omega naught plus alpha t. Here omega naught is 0, initial angular velocity, plus alpha is 1.83. Just we found that angular acceleration. We did find 1.83 into time 2 seconds, 3.66 radians per second. And coming to linear velocity, v is equal to r omega. Here radius is 0.3 meters and omega is 3.66, 1.098 meters per second. And next, tangential acceleration, at is equal to r alpha. Here r is equal to radius of the flywheel, that is 0.3, and alpha 1.83, 0.549 meters per second square, that is tangential acceleration. And radial acceleration, normal acceleration, that is equal to v square by r. V square velocity, v is 1.098 square by, here the radius of the flywheel is 0.3, 4.018 meters per second square. Total acceleration, a square is equal to a n square plus at square, that is here a square is equal to 4.055 meters per second square from the normal acceleration square plus tangential acceleration square. And see the one more problem. The angle of rotation of a body is given by the equation. Here it is given the angle of rotation of a body, theta is equal to 2t cube minus 5t square plus 8t plus 6, where theta expressed in radians and t in seconds. Determine angular velocity and angular acceleration of a body when t is equal to 0 and t is equal to 4 seconds. So here it is given angle of rotation of a body by the equation angular displacement, theta is equal to 2t cube minus 5t square plus 8t plus 6, that is given, with theta is expressed in radians per second. Okay, differentiating this equation, d theta by dt is equal to omega is equal to d theta by dt means omega angular velocity, that is 2t cube 3 into 2 60 square minus 10t plus 8. By differentiating the first equation, we got angular velocity from the angular displacement. Again differentiating the angular velocity, we will get angular acceleration alpha, that is d omega by dt, 12t minus 10. See, in the question it is given when t is equal to 0 and t is equal to 4 seconds, we have to find angular velocity and angular acceleration of the bodies. Here from the displacement equation, we got angular velocity and angular acceleration velocity. By applying the t is equal to 0, in angular velocity, omega is equal to 60 square minus 10t plus t. Here 6 into 0 plus minus 10 into 0 plus 8. Then the angular velocity, omega is equal to 8 radians per second. By applying the t is equal to 0 in angular acceleration, 12 into 0, 0 minus 10, that is minus 10 radians per second. When t is equal to 4 seconds, omega is equal to 6 into 4 square minus 10 into 4 plus 8, and omega is equal to 64 radians per second. Alpha is equal to 12 into 4 minus 10. By applying the t value, that is 4 seconds, alpha is equal to 12 into 4 minus 10.